There are a variety of ways the collision stuff we talked about on Friday gets utilized on the AP exam. However, the collision stuff is almost always a small part of a larger problem. What I'd like for you to do is I'd like you to see kind of the 3 or 4 different ways collisions tend to enter the AP exam. Now, when it comes to momentum, collisions are the number one way momentum is tested on the AP exam. And I don't want to make this all about the AP exam. I really don't. But again, we lost a week. So I'll come back to momentum and more of the importance of momentum when we come back from the break. We'll spend a week or two on it because we'll have time. But right now, I just need you to have the basics. So consider this question. This has been on the exam, I don't know, half a dozen to a dozen times. It's a very common AP question. All right, so either they'll start the brick at the top of some hill, or they'll start the red brick at the bottom of the hill, but pressed up against some spring. They're going to have to give the red brick energy somewhere. So either they'll start it down at the bottom and say that we've got elastic potential energy in the box, or they'll start at the top of this ramp and give it gravitational potential energy. Either way, the point is so that when the box gets to here, it's got a certain amount of kinetic energy. Then there's a collision. A collision in such a way as the two boxes stick together. So what we talked about on Friday is a perfectly inelastic collision. After the collision, the system continues until it makes it through some loop. Generally, the question is asked in reverse order. And they start with, what is the minimum speed necessary for the system to be able to make it through the loop? And then they work the problem backwards. How fast do the bricks have to be traveling after the collision for them to successfully make it to the top of the loop? How fast does the red block have to be going before the collision so that after the collision, the blocks can successfully make it through the loop? How far back against the spring does the block have to be pulled so that when launched, it'll be going fast enough so that after it collides, it can make it through the loop? You see where I'm going? That's a very common question. It's a question in that you have to know when conservation of energy needs to be applied versus when conservation of energy needs to be applied, compared to when neither will work and you'll need net force. This problem, you'll need conservation of energy twice, conservation of momentum once, and net force once. Net force is required to figure out the minimum velocity. You should already know that. We've passed that portion of the exam. That's a combination of net force and centripetal acceleration. We should be aware that there are two forces that act on the boxes, mg and normal force. They combine to produce mv squared over r, and there are limits, meaning it only travels in a circle as long as the forces on the left are balanced by the centripetal acceleration on the right. One of those is a constant. One of those has a minimum. That minimum is 0 for the normal force. That tells you the limits of how fast the system has to be traveling. Back up one step. When the boxes are here, they have gravitational potential energy and kinetic energy. But when the boxes are here, they're at the reference level. And because they're at the reference level, they only have kinetic energy. That's a conservation of energy problem. Although there are two objects here, because they're stuck together, they are effectively a single object moving from one location to another. Everything about it screams conservation of energy. You're interested in the velocity, and the object changes height. Those are your clues that it's conservation of energy. You'll set the state of the energy at this portion of the problem to the state of the energy at that part of the problem. They should be equal. Only in this moment should you be contemplating collisions. When one object contacts and sticks to another, that's a collision. The conservation of momentum part of this problem exists only there. And I'll remind you, something I said in class, it's incredibly important that a collision is the instantaneous moment before contact and the instantaneous moment after contact. So the collision is this instant before they touch. The momentum of these two objects has to be equal to the momentum after they touch. That's the only part of the problem that probably uses momentum. Momentum is not conserved when the boxes are going through the loop. They're experiencing an external force that changes their velocity, gravity. Gravity slows them down. Momentum is not conserved. Energy is conserved. Momentum is not. Momentum is conserved during the collision, and that's the only time we use momentum conservation. Back up one step before that. This block got velocity from somewhere. Sliding down the ramp suggests conservation of energy. Gravitational potential equals kinetic. Being pulled back against the spring, conservation of energy. 1/2 kx squared for elastic potential energy equals kinetic energy. This problem vacillates between conservation of energy, conservation of momentum, conservation of energy again. It's an excellent example, and you'll notice, look at all the things they can pull together in a single problem. And this problem looks a lot of different ways. This is one way that it looks. The other way this problem looks is instead of having a box on a track, imagine a much smaller box. Let me draw it different. A dart strikes a box and the system rotates in a circle. Same kind of problem. How fast would the dart have to be traveling for the system to make a complete circle? There's a minimum. This would be exactly the same problem. Again, one style of the way we'd see momentum problems introduced into the questions. Can you kind of see this question coming? You know, we start the red block either here or against the spring, some way to give it some initial velocity from the start of the problem. So it slides down the ramp or is launched by the spring. So something where I have maybe gravitational potential or elastic potential. That's converted into kinetic energy in the block as it slides across the table. It slides to and connects with the blue block. The two of them travel off the table together, landing someplace over here. That is a projectile problem. You can work this problem from beginning to end or end back to the beginning. How high on the ramp would I have to start the red block so that the two blocks land together a meter away from the edge of the table? But this portion of the problem can be either projectile or a combination of motion equations and energy. This part of the problem is the collision portion. The red box has momentum before the collision. If they stick together, the red and blue box must have the same momentum. The collision is the instant before contact and the instant after contact. Conservation of energy question sits over here. The box has elastic or gravitational potential energy before it's released, and it converts that energy to kinetic after it runs down the ramp or is pushed away by the spring. Fairly standard problems, but the thing about this, it's a 15-minute FRQ that can hit 3/4 or even more of the material that we've covered this semester. So, this one is called a ballistic pendulum. They probably won't refer to it like that anymore because that kind of phrasing has fallen out of favor. They don't actually use this to measure the speed of projectiles anymore. But there was a time when this is how they did it. So generally it's a box hanging on a string. So I need a couple of these for this. So usually what you have is you have two parts of this problem, and they leave out the middle part. You have to conjecture the middle part on your own. So they'll have a dart or bullet or projectile launched at the block, and they say that it becomes embedded in the block, and the block dart system swing upwards until they reach some angle. There's a number of ways they can work these problems out. They can give you the angle first, have you work backwards. They can give you the dart's velocity, have you work forwards. There's even some in which they give something in the middle. This problem is generally a second semester problem and not a first semester problem. I'm telling you this just so you have, knowledge that if you don't see it now, you'll see it later. In the second semester, instead of making it a dart and a block, they'll make it a dart and a larger object that has extension, and they'll indicate or try to get you to indicate what happens to the angle that this makes depending on where you strike the object. They make this about rotational motion and moment of inertia, things we'll talk about second semester. But for the time being, we'll teach this as a point mass problem like this. And here's how I've decided to do this problem. I want you to have some flesh in the game. So I've got a 10-gram dart and a 250-gram block. The dart is fired at 100 meters per second and becomes embedded in the block. What is the maximum angle made by the dart and block? This will be the angle the system makes when it stops before it swings back downwards. So just to make sure we all understand each other, the system doesn't freeze in action here. It swings upwards, stops, and swings backwards. The maximum angle occurs for that instant where the system is stopped. All right, but it doesn't stay there. Gravity will cause it to swing backwards, and it will keep swinging back and forth until air takes all the energy out of the system. Let's assume no air resistance, no friction. Now, these problems generally are an attempt to see if you can identify when one type of thing is conserved versus another. You have to be able to know when momentum is conserved versus when energy is conserved. And they often are leaving out a portion of the problem on purpose. In this problem, they are specifically leaving out the middle of the problem, the instant right after the collision. That's the part that's being left out in the drawing here. And they will do that on purpose. You have to be aware that there are two parts to this problem. There's the collision portion of this problem, which is the instant before the dart touches the block and the instant after the dart touches the block. That's being left out because after that collision, the dart and block are one object that swing upwards. So the first thing I want to do is I want to kind of put in here a middle part of the problem. And that part is the part where the dart is now embedded in the block, but the dart and block have some velocity after the collision. Now, I want to remind you, in these problems, you have to figure out when one thing is conserved versus another. So the first thing I want you to do is I'd like you to figure out the velocity of the dart block system. This is the collision portion of the problem. It's clear it's a collision because one object contacts another and becomes embedded in it. That's how you know it's a collision. Two objects become one. Energy will not be conserved. Momentum will. So please find the velocity of the dart block system after the collision. And if you don't remember because you weren't here on Friday, I'm just going to walk through it as if I'm talking out loud while I'm solving it myself. I've decided this is a collision question. I am setting this direction positive. Before the collision, there was the dart, and it had momentum. And there was the block. It did not have momentum. Assuming no external force acts on the system during the collision, and it doesn't. After the collision, there is one object that is a dart block combination, and they will have the combined momentum of the system. I have set to the right to be positive, and I will be reminded that momentum is mv and is a vector quantity. So to the right has been made positive. And the dart has mass 0.01 kilograms and a velocity of 100 meters per second in the positive direction. The block has zero momentum because it is not moving. There's not more than one kind of linear momentum. There's just one kind. If it's moving, it has it. If it's not moving, it doesn't. However, after the collision, the dart has become embedded in the block, so they move together as if they were one object with a single mass, and they have one velocity. It is your responsibility now to find what the size of that velocity is. That's the momentum portion of the problem. Assuming they knew what they were doing last class period, 3.85 meters per second. And I'm not surprised. This is 1 divided by 0.26. It's going to be a little less than 4. Now, you need to do something else just to make sure you're really paying attention. How much kinetic energy is lost in this collision? You can figure that out. You should have no trouble with that question. We've talked about it before. How much kinetic energy is lost? But I'll say again, the amount of energy in the system stayed the same. So I know how much kinetic energy I have right after the collision. And since the darts and blocks swung upwards, they stored that energy in gravitational potential. I know the energy has to be the same because the only two forces acting on the block is gravity, a conservative force, and tension. And tension does not do work on the system because it's perpendicular to the displacement of the block. I'm repeating this all because I forgot to hit record. But you should be halfway through finding my answer. And I hate the fact that I'm going to write this up here because you guys refuse to memorize things, but that little thing right there could probably help you figure out the angle. You'll need something that you don't have. What is it that you need? You need the length of the string holding the block. That's what L is. Let's go with 2 meters. 2 meters. Now you got something you can do. all the heavy liftings on the board. You're looking for theta. You can do this. Try it. I don't want to spend a lot of time pushing buttons. Assuming everything works out, you're getting an angle. Now look, there's lots of ways this might not work out, which is why I want you to work the numbers. I want you to see the possibilities. There are lots of ways this doesn't work out. Now, I'm putting this here because I want you to do the math, but understand that there are limits here. Now, there's not every possible answer here. If we look, we're going to be subtracting something from both sides and then dividing by this. When I take 1.93 and subtract 5.2, I get negative 3.27. That equals negative 5.2 cosine theta. Now, yeah, you can solve this for theta, and you should. And it works. But it works because this number is smaller than this number. And it also works because it happens to be positive. Those are two very necessary things. Because look, in the real world, you might get an answer that doesn't seem to match your expectation. Would result in no answer for theta, and you need to think about what that means. Can you imagine a problem in which the dart is traveling fast enough where the whole system actually revolves around this? It is possible, of course it is. Now, the reason that's important is that that would mean that there is no angle for theta that works here. It never stops. You'll see that in your math. You will get no answer for theta. That possibility exists. You need to be prepared for that. What do you do when that happens? You can also probably imagine that there are thetas that are greater than 90 degrees. And that would also be okay. What does that mean for your possible answer? So these are things that can occur. You need to be expecting them. All right. I know you don't believe what I'm about to say here, but this is relatively a vanilla question. It's got a lot of stuff in it, but it really isn't all that interesting. It's 1 part conservation of momentum, 1 part conservation of energy, and a little geometry thrown in. This is unlikely to be on the test because it's too simple. It would have to be part of a larger problem. So we're back to our roller coaster problem. I'm not trying to hurry you along, but again, we already know how fast we have to be going at the top of the loop. We have that minimum speed. We must be going at least that fast at the top of the loop. If I want to figure out how fast they're going at the bottom of the loop, then I probably should use conservation of energy. Why? Because the telltale signs are here. The object travels in a circular path, so the path's independent nature of gravitational potential energy helps. The fact that we are changing height and there's no external force on the system that takes energy away, no friction, stuff like that, that says conservation of energy. And the fact that there are 2 distinct states that we are comparing, top of the loop and bottom of the loop. Lastly, why energy? Velocity is involved. Energy is all about velocity and position. So I'm saying all that. Who has the answer here? You should be almost done. A whole lot to go on. There's not a whole lot to do here. At state A, am I at the reference level or above the reference level? So there is no gravitational potential energy at state A. Is the object moving at state A? Sure is, so I'm definitely going to have kinetic energy. Let's move on to state B. Am I above the reference level when I'm at state B? Sure am. I am 2r above the reference level. 2r above the reference level, right? I am a diameter above the ground. And am I moving at state B? Yes, I have to be. If I'm not moving at state B, I can't be in circular motion. That was the whole point of question number 1. Question number 1 is a gift to you to help remind you that you have to have some velocity or you can't be in circular motion. Don't think of it as a chore. They're reminding you about that. They don't have to ask that question at all. They could ask question 2 on its own. How fast you have to go at the bottom to successfully make it through the loop and not remind you that you have to be moving at the top of that loop or you can't travel in a circle. So that means 2mg times 2r plus 1/2 times 2m times v, which is square root of gr squared. That's the energy at state B. That has to be equal to the energy at state A. 1/2 times 2m times v at the bottom squared. I'm noticing all the 2m's will cancel out. How convenient. That leaves me with 2gr plus, this one's a little hard, 1/2 times the square root of gr squared. So 1/2 gr. And that has to equal 1/2 v bottom squared. So here's where I misspoke a little bit, but this is 5/2 gr equals 1/2 v bottom squared. So v bottom is the square root of 5 gr, not 5/2. Forgot about multiplying by 2. I like this for a number of reasons. First, that's the speed at the top of the loop. That's the speed at the bottom of the loop. I'm glad that one is less than the other. And it's all in terms of GR. I didn't know that to expect that the first time I saw this, but I'm glad it is. That's why everything adds up so nicely and neatly. And that's why they ask these kinds of questions on the exam. Now, I've only got a few more minutes left, not even a few. But do you see the collision that has to take place now? This is the before case. There's going to be the red box sliding down the ramp just before the collision, right here. After the collision, it has to be traveling that fast, both blocks. So before the collision, mv. After the collision, 2m times the square root of 5gr. There's no way to make this neater. Cancel the m's, and the velocity's got to be twice as big before the collision because tons of energy is lost during that collision. Now, we didn't get to the end here, but I don't think it takes too much for you to compare the kinetic energy of the block before the collision with the elastic potential energy that block must have had when it was against the spring. Be careful. This portion of the problem is about 1 mass, not 2. So the kinetic energy is 1/2 m 2 times the root of 5gr squared. That equals 1/2 kx squared. Look, I'm going to post a practice